A city with no lights. A highway with no traffic. A world with no human sound. This is the earth not as it healed, but as it fell silent. The silence here is a heavy, oppressive thing. A pressure on the ears that speaks of a profound and final absence. Our steel towers, monuments to our own fleeting dominance, stand corroded and skeletal, slowly being strangled by vines. But this green is a lie. It is a veneer of life on a world suffering from a terminal illness. The real legacy we left behind is not in these ruins of concrete and glass. It is invisible. It is in every breath of air, every drop of water, every grain of soil. We are gone, but our chemical ghost remains, haunting the very machinery of the planet. For this is not a world being reclaimed. It is a world saturated with poison. We manufactured chemicals designed never to break down. Persistent organic pollutants that seeped into the water table and accumulated in the fat of every living thing until there were no living things left. We created plastics so durable they have now formed a new, permanent layer in the planet's geology, a fossil record of our convenience. But these were just localized poisons. The true masterstroke of our destruction was global. We fundamentally changed the sky. We took carbon that the planet had spent 300 million years carefully burying, and we set it on fire in the space of 2 centuries. The atmosphere we left behind was a glass coffin. Before our industrial age, the air held a stable 280 parts per million of carbon dioxide. By the time we vanished, that number had soared past 420, and the planet's temperature had become locked in a runaway cycle. The elegant, planetary-scale breathing that had kept Earth in a delicate equilibrium for eons was shattered. The atmosphere became a one-way mirror, letting sunlight in but refusing to let the heat escape. The forests, our great allies in breathing, were decimated and overwhelmed. They could no longer absorb the sheer volume of our atmospheric waste. The planet was suffocating, slowly and inexorably, under a blanket of our own making. But the true horror, the epicenter of the extinction, was the ocean. It was our planet's greatest defense, absorbing nearly a third of the carbon we unleashed. This act of salvation, however, was a suicide pact. When carbon dioxide dissolves in seawater, it forms carbonic acid. Over mere decades, the ocean's pH dropped from a stable 8.2 to 8.1. Because the pH scale is logarithmic, this tiny-sounding shift represented a staggering 30% increase in acidity. The ocean, the cradle of all life, was turning corrosive at a rate faster than anything in the geological record. We had declared chemical warfare on 2/3 of our own planet. So what happens when an entire ocean becomes acidic? The result is not just death. It is a planetary-scale starvation. Life in the sea had spent eons evolving to build shells, skeletons, and reefs from calcium carbonate. But in this new, acidic water, the essential building blocks, the carbonate ions, were becoming impossibly scarce. The carbonic acid was stealing them, hoarding them away. For every microscopic pteropod, every tiny foraminifera, every reef-building coral, it was like trying to construct a house while a thief was actively stealing your bricks. Their bodies, their homes, their very existence demanded a material the ocean could no longer provide. This was the great unraveling. It began with the smallest, the invisible architects of the sea. The pteropods, delicate sea butterflies at the base of polar food webs, began to dissolve. The foraminifera, whose shells create entire beaches and seabeds, vanished. Then the coral reefs, the vibrant cities of the ocean, began to bleach and crumble, leaving behind vast, bone-white graveyards. This was a systemic osteoporosis of the sea. Without this foundation of calcifying organisms, the entire food web collapsed from the bottom up. The fish that fed on them starved. The predators that hunted those fish disappeared. The great whales were left to patrol a silent, empty abyss that offered no sustenance. How does a planet heal when its very chemistry has been rewritten? Can't. The carbon cycle, the planet's circulatory and respiratory system, was fundamentally broken. We hadn't just clogged the Earth's lungs, we had paralyzed them. The natural carbon sinks, the oceans and soils were saturated to their breaking point. Worse, we had triggered irreversible feedback loops. The warming we initiated was now causing the Arctic permafrost to thaw, releasing colossal plumes of methane, a greenhouse gas dozens of times more potent than CO2. The planet was no longer just suffering from our initial injury. It was now caught in a cascade of self-inflicted wounds. The silence on the surface became the defining feature of this new era, the Anthropocene. It was the quiet of a world caught in a state of suspended animation, a death grip of our own design. There was no longer a pathway to recovery, no simple way for nature to bounce back. The system was too overloaded, the chemical damage too profound. The planet was like a complex engine that had been fed the wrong fuel for too long. Every component was corroded. Every gear was grinding to a halt. It was stuck. It needed a shock, a force powerful enough to shatter the broken equilibrium and start again from zero. It needed a power that came not from the sky, but from the fiery heart of the world itself. For millennia, the surface of the Earth languished in its poison stasis. But the silence was a lie. Deep beneath the dead oceans and the sterile continents, the planet was anything but quiet. The Earth's core, a sphere of solid iron hotter than the surface of the sun, radiates a colossal, unceasing heat. This energy churns the molten mantle above it in slow, powerful convection currents, a geological engine that has been running for over 4 billion years. This is the engine of plate tectonics, a force so immense it makes our entire civilization look like a fleeting breath on a winter morning. It is a force that feels no pity, observes no history, and obeys only the laws of physics. While our world decayed on the surface, this deep engine was building pressure. The slow dance of continents, the grinding of tectonic plates, had not stopped. Heat was pooling beneath the crust, weakening it from below, like a slow fire held under a sheet of ice. The planet was developing a fever in its very bones. This was not a response to our presence or our absence. It was the indifferent, relentless continuation of a process that has shaped and reshaped the world countless times. The planet's pulse was quickening, and it was about to enter a new, violent phase of its life cycle. The change didn't announce itself with a single, dramatic explosion. It began as a tremor in the deep earth, a planetary-scale spasm. This was the dawn of a new age of fire, driven by the formation of what geologists call large igneous provinces. These are not your typical cone-shaped volcanoes. Instead, imagine the Earth's crust cracking open like an egg along fissures hundreds of miles long, unleashing biblical floods of ultra-hot, low-viscosity basaltic lava from the mantle. This wasn't an eruption. It was a hemorrhage of molten rock. The planet was literally bleeding fire onto its own surface, an act of creation so violent it would first have to unmake the world we knew. So how does a planet on fire get cold? This is the great paradox of a volcanic age. As these massive fissure eruptions tore open the crust, they vented trillions of tons of gases directly into the atmosphere. Among them was carbon dioxide, the very poison that had broken the world in the first place. But they also belched something else in far greater quantities: sulfur dioxide. Launched with explosive force, this gas rocketed high into the stratosphere, an upper atmospheric layer far above the clouds and weather. Here, it began a chemical reaction that would change the fate of the world. In the cold, thin air of the stratosphere, the sulfur dioxide gas bonded with water vapor. The result was a fine, shimmering mist of sulfuric acid aerosols. These microscopic droplets were incredibly reflective. They began to scatter and reflect incoming sunlight back into space, increasing the planet's albedo, or its total reflectivity. We have seen small-scale versions of this in our own time. The 1991 eruption of Mount Pinatubo cooled the entire planet by 0.5 degrees Celsius for 2 years. Now, imagine 1,000 Pinatubos erupting continuously for 10,000 years. The effect was a planetary sunshade, a global chemical mirror that blocked a portion of the sun's energy from ever reaching the surface. The world, which had been trapped for so long in a suffocating greenhouse, began to cool rapidly. This volcanic winter was a brutal, planetary-scale shock to the system. It was the planet throwing itself into a state of artificial ice age to break the fever of the runaway greenhouse effect. The long-term warming from the volcanic CO2 was still a threat, but it was a problem for a distant future. The immediate, overwhelming effect of the sulfate aerosols was a deep and persistent cooling. The heat was trapped above the shield, while the surface shivered in a volcanic twilight. But the true change was happening on the ground. For thousands of years, the floods of basalt continued. These were not slow, creeping lava flows. They were fast-moving rivers of fire that advanced at the speed of a running person, covering everything in their path. They buried our dead cities under 1,000 feet of black rock. They filled entire valleys, vaporized rivers, and spilled into the oceans with a violent hiss of steam, creating new coastlines. The map of the world was being aggressively redrawn, not with ink, but with fire. The planet was cauterizing its own wounds, entombing our entire poisoned civilization under a new, clean crust. This new rock was more than just a burial shroud. It was a chemical transfusion for a dying world. Basalt, forged in the pristine, high-pressure environment of the Earth's mantle, is incredibly rich in reactive minerals, silicates, iron, magnesium, and phosphorus. The surface of our world had become depleted, its soils exhausted and polluted. This was a delivery of fresh, virgin material on a continental scale. This black, sterile rock held the very elements needed for the next stage of the planet's recovery. It was a blank slate, a chemical reset button waiting to be pressed by the one thing that still fell from the sky: the rain. For centuries, the world existed in a state of profound contradiction. The sky, veiled by a stratospheric haze of sulfur, was cold. The surface, paved with fresh, black basalt, still radiated a deep, primordial heat. This was a world caught between fire and ice, a planet in a state of violent transition. The Great Volcanic Act was not a single event, but a new status quo. And within this dramatic new environment, a process far quieter, yet infinitely more powerful than any eruption, began. The true work of rebuilding the planet would not be done with explosions and lava flows, but at a molecular level, through a slow, silent conversation between rock and water. The agent of this change was the rain. It fell from the cold, hazy sky, not as clean, pure water, but as a weak acid. The atmosphere was still saturated with legacy carbon dioxide, and as water condensed, it reacted with the CO2 to form carbonic acid. For eons, this had been the very acid that corroded the oceans and destroyed the base of the marine food web. But now, falling upon this new volcanic landscape, this acidic rain was no longer a poison. It was a key. It was the solvent that would begin to dissolve the world's problems, one drop at a time. But how do you clean a sky with nothing but rock and water? The answer lies in the unique chemistry of the rock itself. The basalt that now covered millions of square miles was incredibly rich in silicate minerals like pyroxene and feldspar. These minerals are forged in the high-pressure, oxygen-poor environment of the mantle. On the surface, they are chemically unstable and therefore highly reactive. As the acidic rain fell upon these vast, black plains, a chemical reaction known as silicate weathering began. It was a slow-motion chemical reaction the size of a continent. Think of it as the planet taking a colossal antacid. The carbonic acid in the rain landed on the calcium and magnesium silicates in the basalt. The acid reacted with the rock, breaking down its crystalline structure. In this process, the carbon dioxide that had formed the acid was transformed. It was pulled directly out of the atmosphere and locked into a new, stable, water-soluble molecule, the bicarbonate ion. Every single raindrop that struck the new land became a tiny chemical hook, snatching a molecule of poison from the air and neutralizing it. It was impossibly slow, but it was happening everywhere, all at once. This was not a temporary fix. It was a one-way ticket for carbon into the deep earth. As the rocks weathered, they released their mineral components, and the newly formed bicarbonate ions flowed into streams and rivers. The waterways of this new world ran milky, not with pollution, but with dissolved rock and captured carbon. They carried this immense chemical load towards the oceans. This journey was the second crucial step in permanently sequestering the carbon that had choked the world for so long. Once in the ocean, this influx of calcium, magnesium, and bicarbonate ions would eventually be used by marine life to build shells. When these organisms died, their shells would sink, forming a constant marine snow. Over millions of years, this sediment would be compressed by the weight of the ocean above, hardening into immense layers of carbonate rock, limestone, dolomite. The carbon that was once a gas, trapping heat in the atmosphere, was now being turned back into solid stone. It was being returned to the geosphere, buried, and locked away for hundreds of millions of years. The planet was slowly, methodically, breathing through its skin of rock. While this great chemical scrubbing was cleaning the air, another volcanic gift was healing the seas. The most explosive eruptions had thrown quadrillions of tons of fine ash into the atmosphere, and for centuries, this black snow fell continuously across the globe. Its most important destination was the vast, barren surface of the oceans. To a world starved of life, this ash was manna from the heavens. It was a comprehensive fertilizer, packed with every essential element life needs, from phosphorus and nitrates to magnesium and potassium. But its most critical component was iron. The oceans of the Old World had become what scientists call high-nutrient, low-chlorophyll zones. They had plenty of the major nutrients, but they were barren deserts because they lacked the one crucial micronutrient that unlocks photosynthesis in phytoplankton: bioavailable iron. This ash, being pulverized volcanic rock, was rich in it. As the ash rained down upon the Dead Seas, it dissolved, injecting a steady, global dose of iron into the sunlit surface waters. It was the key that the ocean had been missing, the spark needed to ignite a biological fire. The stage was now set for the planet's second act of genesis. The great fertilization had primed the oceans, creating a nutrient-rich chemical soup waiting for life to bloom. Simultaneously, the great weathering was slowly but surely drawing down the atmospheric carbon, relieving the greenhouse pressure and stabilizing the climate for the long term. The planet's chemistry was being fundamentally rewired. The system had been shocked, cooled, and then methodically cleaned and reseeded. The violent, fiery phase was over. Now, the silent, patient, and far more transformative biological phase was about to begin. The chemical stage was set. The oceans, once a sterile, acidic desert, were now a vast, nutrient-rich broth, seeded with volcanic minerals and bathed in the pale light filtering through the stratospheric haze. For centuries, this potential lay dormant, a quiet promise of life waiting for a spark. And then it happened. The few hardy species of microscopic phytoplankton that had survived the Great Extinction found themselves in a world perfectly engineered for their explosive growth. The survivors, perhaps resilient diatoms and coccolithophores, began to feast on the sudden abundance of iron, nitrates, and phosphates. What began in scattered, sunlit patches of the ocean surface quickly erupted into a coordinated, global event. It was the Great Bloom, an explosion of life so immense it fundamentally began to terraform the planet for a second time. The diatoms, tiny single-celled algae with intricate silica shells, multiplied in their trillions. Coccolithophores, covered in tiny calcium carbonate plates, clouded the seas in vast, milky white blooms. Within a few thousand years, the desolate blue of the oceans was replaced by a vibrant, swirling canvas of green, turquoise, and white, a living Jackson Pollock painting visible from space. The planet was breathing again, and this was its first, deep, shuddering breath. So how does a microscopic plant become the most powerful climate-altering force on Earth? It does so through sheer numbers. This new, global forest of algae began doing what all plants do: photosynthesis. They inhaled the carbon dioxide that still saturated the upper ocean and, using the energy of the sun, converted it into organic matter. The waste product of this reaction was oxygen. A fresh, cleansing wave of it began to pour into the atmosphere, slowly detoxifying the air. But the true miracle was what happened to the carbon they absorbed. It became the fuel for a planetary-scale carbon sequestration machine. This machine is known as the biological carbon pump, and it is one of the most elegant and efficient systems on the planet. As the trillions of diatoms and other phytoplankton lived their short, frantic lives, they incorporated the carbon from the water into their own bodies and shells. When they died or were eaten, they began to sink. This wasn't just a few dead cells. It was a constant, gentle, and globe-spanning snowfall of organic matter. Scientists call it marine snow, a delicate cascade of dead algae, fecal pellets from tiny animals, and other biological debris, all rich in captured carbon. This marine snow began its long, slow journey into the abyss. It fell through the mesopelagic zone, the ocean's twilight zone, a realm of crushing pressure and fading light between 200 and 1,000 meters deep. Here, a portion of the snow was consumed by a host of strange creatures adapted to the semi-darkness, which in turn repackaged the carbon and sent it further down. But the sheer volume of the bloom was so immense that the twilight zone ecosystems couldn't possibly consume it all. A significant fraction of the carbon-rich material continued its descent, falling past the last rays of sunlight into eternal darkness. Its final destination was the abyssal plain, the vast, flat, and crushing darkness of the deep ocean floor, miles below the surface. Here, the marine snow finally came to rest, forming a thick, carbon-rich ooze. Over thousands of years, this layer of organic sediment grew, compacted by the immense pressure of the water above. This was the final stage of the process. The carbon, which had once been a heat-trapping gas in the atmosphere, was now part of a dense sludge on the ocean floor. Eventually, over geological time, this ooze would be buried and compressed, becoming black shale and other carbon-rich sedimentary rocks, locking the poison away for hundreds of millions of years. It was a carbon escalator to the abyss. But what if life never needed the sun at all? While this sun-powered revolution was transforming the surface, a completely separate and arguably more resilient form of life was thriving in the deep darkness. The renewed volcanic activity had created thousands of new hydrothermal vents on the seafloor. These black smokers are jagged chimneys that spew a superheated, toxic brew of chemicals directly from the Earth's mantle. In this seemingly hellish environment, devoid of light and packed with heavy metals, life had found another way. This was the dark genesis, running on the planet's inner fire. Instead of photosynthesis, life here is powered by chemosynthesis. At the base of this food web are ancient bacteria. They harness the chemical energy locked within the hydrogen sulfide, a gas that smells of rotten eggs and is lethal to most surface life, that billows from the vents. They oxidize this chemical to create the energy they need to live, becoming the producers in a food web that is completely alien to the sunlit world. Around them, an entire ecosystem had evolved, a bizarre menagerie of life built for pressure and poison. Giant tube worms, some over 2 meters long, with no mouths or stomachs, survive on the bacteria packed inside their bodies. Blind, white crabs scuttle over the chimneys, and ghost-like fish navigate the toxic clouds. The planet was now being reborn on two fronts. On the surface, a massive, sun-fueled biological engine was scrubbing the atmosphere and rebooting the marine food web. In the depths, a dark, chemical-fueled engine was preserving life in secret bunkers, creating evolutionary experiments in the most extreme environments imaginable. Life wasn't just recovering. It was attacking the problem from above and below. This two-pronged approach guaranteed its ultimate success, creating a world teeming with potential and ready for the next, most creative stage of its rebirth. The explosion of new forms to fill a world that had been wiped clean. Let us jump forward in time. Not by centuries or even millennia, but by millions of years. The volcanic age has long since passed into geological memory. The violent, formative period of fire and ash has given way to a new, profound stability. The sky is no longer a hazy veil but a brilliant, unfamiliar shade of azure, its atmosphere rich with the oxygen produced by the great blooms. The oceans are a deep, clear blue, their chemistry now governed by a new and resilient biosphere. The long, slow work of weathering and biological sequestration has succeeded. The planet's fever has broken, and its climate has settled into a new, stable equilibrium. This is the climax of Earth's recovery. But it is not a restoration. It is a genesis. The world is stable, the air is clean, the oceans are full. But they are also empty. The mass extinction we caused was so absolute that it did more than just kill species. It erased entire ecological roles from existence. The niches of the apex predator, the massive herd grazer, the treetop browser, the burrowing scavenger. All of them were left vacant. The planet had become a furnished mansion with 1 billion empty rooms, a kingdom with 1,000 vacant thrones. Life, for the first time in hundreds of millions of years, had been given a blank canvas. So what does life do when it is given a world of endless opportunity and zero competition? It undergoes one of the most spectacular processes in nature: adaptive radiation. It's evolution's gold rush. We have seen small-scale versions of this on Earth before. When a few finches landed on the pristine Galapagos Islands, their descendants evolved into over a dozen distinct species, each perfectly adapted to a different food source. When ancient fish colonized the African Great Lakes, they exploded into thousands of species, filling every role from algae scraper to apex predator. Now, imagine that process not on an island or in a lake, but across an entire planet. The few species that survived our extinction, the hardy, the small, the deep ocean dwellers, became the founders of this new world. They were like the winners of a cosmic lottery, emerging from their bunkers into a paradise built just for them. A creature that was once a humble, nocturnal insectivore could now find itself in a world with no large predators and endless vegetation. Its descendants could, over generations, grow larger, shift their diet to plants, and eventually evolve to become the new megafauna, the 6-ton grazers of this new Earth. This is evolution with the brakes taken off. The new atmosphere itself dictated new evolutionary paths. The immense, sustained phytoplankton blooms had pumped the air full of oxygen, perhaps reaching concentrations not seen since the Carboniferous period 300 million years ago. For animals with inefficient respiratory systems like arthropods, this was a game-changer. The descendants of spiders, centipedes, and insects were no longer constrained by a lack of oxygen. On this new Earth, dragonflies with the wingspans of eagles could hunt through the treetops, and scorpion-like predators the size of wolves could stalk the forest floor. The age of mammals had ended. The age of something else entirely had begun. And in this biological Big Bang, nature began to rediscover its favorite blueprints through a process called convergent evolution. This is the phenomenon where unrelated species independently evolve similar traits to solve similar problems. The streamlined, torpedo-like body of a predator is an incredibly efficient design for moving through water. While the sharks and dolphins we knew were gone, the ocean would still need an apex predator. Perhaps a lineage of squid, abandoning their soft bodies, evolved an internal, cartilaginous skeleton and a powerful tail, becoming a creature that looked and hunted remarkably like a shark, but was born from a completely different branch of life. The same pattern would repeat across the globe. The role of the soaring bird of prey might be filled by a new species of giant, predatory bat. The niche of the herd-grazing bison could be taken by a new form of giant, land-dwelling tortoise that had evolved to be warm-blooded. Evolution is not sentimental. It does not remember what came before, but it is ruthlessly efficient, and a good design will often emerge more than once. The world was being repopulated with familiar ghosts wearing completely new faces. But this new life was also being shaped by the new geology. The vast plains of basalt, now weathered into strange, mineral-rich soils, gave rise to flora we would find utterly alien. Perhaps plants evolved to incorporate the abundant silica into their biology, creating forests of glittering, glass-like trees with leaves that shimmered like oil on water. Animals living on these plains might have evolved hardened, iron-infused skin or hooves to cope with the sharp, abrasive ground, becoming living sculptures of stone and flesh. The new geography, carved by fire and tectonic shifts, created thousands of isolated evolutionary laboratories. New mountain ranges split continents, trapping populations on either side and forcing them down different evolutionary paths. New inland seas formed, creating massive saltwater lakes where life could evolve in complete isolation for millions of years, becoming ever more strange and specialized. The world had been shattered and remade, and now its very bones were directing the flow of evolution, creating a diversity of life far richer and more bizarre than what had come before. This was the new equilibrium, a world teeming with creatures both eerily familiar and wildly fantastical. A biosphere built by survivors, designed by opportunity, and forged by the planet's new chemistry and geography. It was a masterpiece of resilience, a testament to the relentless, creative power of natural selection. The planet was not just alive again. It was more vibrant, more strange, and more magnificent than ever before. The climax of this story is not one of mere survival, but of spectacular, unimaginable creation. Let us look upon the Earth one last time, not millions, but 100 million years after the silence fell. The world is an alien planet. The continents, in their slow, inexorable dance, have continued their journey. Africa has sutured itself to Europe, crushing the Mediterranean into a skyscraping mountain range grander than the Himalayas. Australia has collided with Southeast Asia, and the Americas are beginning their slow return journey towards the supercontinent of the future, a new Pangaea. The very map of the world, a geography we considered eternal, has been rendered a forgotten dream. Even the stars in the night sky are different, our familiar constellations warped into new shapes by the slow drift of suns through the galaxy. This is the final resolution. The planet is not healed. It has been fundamentally remade. It is a world that has forgotten us in every conceivable way. The biosphere of this new Earth is a mature, complex, and deeply interconnected system, ruled by life forms born from the crucible of extinction and forged by a different geology. The dominant intelligence may not be a single species, but a collective consciousness of massive, continent-spanning fungal networks. The oceans may be ruled by the descendants of cephalopods, creatures of immense intelligence and grace, communicating through vibrant, shifting patterns on their skin. This world's symphony is one we could never comprehend. So is there anything of us left at all? Only a scar in the rock. Future geologists of this world, or perhaps alien explorers sifting through the strata, would eventually find it. A strange, impossibly thin layer in the planet's crust. The Anthropocene layer. It would be a global puzzle box. Within this stratum, they would find bizarre, unnatural concentrations of plastic polymers, the faint radioactive signature of our nuclear follies, and peculiar spherules of burnt fossil fuels. They might even find the fossilized geometric impressions of our buried cities. To them, we would not be a civilization. We would be a geological event, a brief, violent, and inexplicable anomaly in the planet's deep history. What would they conclude from this layer? They would see evidence of a global biosphere crisis, a sudden spike in carbon, a mass extinction, the abrupt appearance of novel materials. They might theorize that the planet was struck by an asteroid or suffered some other external catastrophe. The idea that the planet's own dominant species was responsible might seem so illogical, so completely self-destructive, that it would be dismissed as a fringe theory. Our entire existence, our art, our love, our wars, our gods, would be reduced to a confusing chemical signature that speaks only of a sudden planetary-scale fever. For this new world is not just alive. It is a single, integrated organism. The biosphere that has evolved is deeply intertwined with the planet's geology and atmosphere, creating powerful regulatory feedback loops that make the old world look clumsy by comparison. This is the ultimate expression of the Gaia principle, a system where life actively maintains the conditions for its own survival. The new forests of crystalline flora and the vast mats of oceanic algae regulate the atmospheric gases with ruthless efficiency. The planet's climate is no longer a chaotic system on the edge of collapse. It is a finely tuned engine, managed by a biosphere that evolved in harmony with it. This new world is so stable it even takes the great cosmic cycles in its stride. The Earth continues its long, slow wobble on its axis and the gentle stretching of its orbit, the Milankovitch cycles that drove the ice ages of our time. On this remade Earth, these cycles still occur. But the biosphere is so resilient and interconnected that it adapts gracefully. As the ice caps advance, life migrates and evolves. As they retreat, it follows, recolonizing the land with breathtaking speed. These great climatic shifts are no longer catastrophic. They are merely the slow, deep rhythm to which the entire planet now dances. This brings us to the ultimate, humbling perspective. Our time on this planet was not a grand epic. It was a brief, violent, and cautionary tale. We saw ourselves as the masters of the world, the pinnacle of evolution. But in the context of deep time, we were a planetary disease. the fever. And the planet's immune system, its deep geological and biological processes, was the cure. The volcanoes, the weathering, the blooms, these were not acts of revenge, but the methodical, impersonal response of a complex system purging a destabilizing element. The Earth does not miss us. The universe does not note our absence. The silence we left behind was eventually filled with a new and more resilient song. The story of this planet is not, and never was, our story. It is the story of the Earth itself. We were just one chapter, a dramatic and tragic interlude, before the main narrative resumed. The planet is the protagonist, and its story is one of immense, unceasing resilience, a 4.5 billion-year epic of creation, destruction, and spectacular rebirth. So in the end, we are left with a final, profound question. If a world is so completely remade that no trace of its past consciousness survives, and no memory of what was lost is carried forward, what was the meaning of that first world? We were a species that learned to write, to dream, and to reach for the stars. But we failed to learn how to endure. The ultimate legacy we left was not what we built, but the lesson that the Earth's ability to create is infinitely greater than our capacity to destroy.